Welcome to this explainer. Today, we're diving into the absolute rigorous scientific detective work behind proving exactly how green a product truly is. We hear words like sustainable and eco-friendly thrown around literally all the time, but how do we actually measure the true environmental cost of the things we buy? Well, the secret lies in a fascinating framework called Life Cycle Inventory, or LCI.
Here is our roadmap for today's audit. We'll be hitting the basics of LCI, the laws of nature, mapping the flow, the energy demand, transport and utilization, and finally, the allocation puzzle.
All right, let's jump right into Section 1, the basics of LCI, where we define exactly what we're measuring.
So, at its core, an LCI is a highly structured material and energy analysis based on strict ISO standards. It refuses to leave any environmental stone unturned. I want you to think of it like a massive, incredibly detailed ledger. But instead of tracking dollars and cents, we are relentlessly tracking every single gram of raw material and every single joule of energy that goes into making, using, and eventually disposing of a product.
The fundamental building block of this whole analysis is what we call the unit process. Basically, inputs like raw materials, pre-products, and energy go in, and then outcomes are product, along with waste heat and emissions. Whether this is a giant stamping press in a car factory or just a single chemical reaction in a lab, this is the exact cell where we collect our data.
Which brings us to Section 2, the laws of nature. Because let's be real, we absolutely cannot cheat thermodynamics. Before we start connecting these unit processes together, we have to anchor our methodology. Every single audit must mathematically balance the input and output equations based on 5 foundational principles. We rely on the conservation of mass and energy, the increase of entropy, the strict proportions of stoichiometry, and even Einstein's equivalence of mass and energy. Nature's laws dictate that the mass going into our unit process must exactly equal the mass coming out.
What's really fascinating about this framework is how it establishes absolute, undeniable trust in the inventory process. Technically attainable yields in a factory can literally never be higher than what these scientific equations predict. It sets a hard, undeniable ceiling on manufacturing efficiency. If the data claims otherwise, well, we know something is missing from the audit.
Let me give you an example. Melting just 1 single kilogram of aluminum requires an absolute theoretical minimum of 0.983 megajoules of heat. That's just the baseline physics of it. But the messy, energy-hungry reality on the actual factory floor is always much higher due to unavoidable thermal losses, like heat just escaping into the air. Nature gives us the baseline. The LCI tracks reality.
All right, let's move on to Section 3, mapping the flow.
We always want to start simple, right? Mapping the product tree as a linear chain of unit processes, step by step. Process 1 feeds into process 2, which feeds into 3, and so on. Honestly, if manufacturing was actually this straightforward, doing an environmental audit would be an absolute breeze.
But the reality of manufacturing escalates super quickly. Multiple pre-products and materials branch into the main chain to create a multi-input process. Suddenly, to account for just one unit process, we have to look sideways. We have to trace all those extra materials all the way back through their own separate complex chains. This complexity absolutely blows up when producing something like LAS, a very common detergent ingredient. Just to audit a single kilogram of this final chemical, you have to trace hundreds of kilograms of inputs backward to their cradles. Think about it. The extraction of crude oil branches through a refinery, splits into different chemicals, and eventually merges with mined salt. And every single step of the way requires its own strict energy and mass audit.
That brings us to Section 4, the energy demand.
Of course, moving and transforming all of those materials across that giant web takes a ton of power. So environmental accountants have to calculate the cumulative energy demand, or CED. This means we aren't just tracking the final energy, like the electricity you use at the plug to run a machine, but the massive, hidden primary energy required to extract the fuel, build the infrastructure, and generate that electricity in the first place. If your factory runs on electricity, the CED forces us to ask, what burned to make that electricity, and how much energy was lost in the transmission lines just getting it here?
To get this exactly right, we rely on hard technical data, like the lower and higher heating values of fossil fuels. These values differ depending on the exact chemical makeup of gasoline, methane, or coal. Methane, for instance, yields a higher specific energy per kilogram than coal. Knowing these exact numbers is completely essential for translating the physical mass of a fuel burned into the exact thermal energy it injects into our product's life cycle.
But here's the kicker. Energy isn't just about the fuel itself. It's about geography.
We absolutely have to factor in the regional electricity mix. Pulling a kilowatt-hour from a grid dominated by fossil fuels, like the European mix from 2005, for instance, has a vastly different environmental burden than pulling it from a hydropowered grid in Norway. Incredibly, a product made in one country might have double the carbon footprint of the exact same product made right across the border, simply because of the local power grid.
Next up is Section 5, Transport and Utilization.
So, once a product is actually made, it has to move from the factory to the warehouse and eventually to you. And when assessing transportation, we don't just measure distance. A truck driving 100 miles isn't enough information. Instead, we measure ton-kilometers. This combines the mass of the cargo with the actual distance traveled. Why is this so crucial? Well, transporting a ton of feathers takes up way more space than a ton of steel, which heavily affects how many trucks you're actually going to need on the road.
The math on this is honestly staggering. An empty 40-ton truck burns a massive 9.29 megajoules of energy per kilometer just dragging its own dead weight down the highway. But when that exact same truck is utilized at 100% capacity, the specific energy consumption plummets to a mere half a megajoule per ton kilometer. Logistics matter deeply. Half-empty trucks rapidly inflate a product's overall energy demand.
And finally, we arrive at Section 6, the allocation puzzle.
Up until now, we've relied on the strict laws of thermodynamics to balance our ledgers. But those hard and fast rules hit a massive roadblock when a single unit process spits out several usable products at the exact same time. This is called a multi-output process. Imagine a dairy factory. Raw milk goes in, but cream, skim milk, and butter all come out. They are co-products. So how in the world do you divide the environmental cost of the cow among the butter and the milk?
This problem, which was actually first noted by the philosopher Stuart Mill, creates an incredibly tricky scenario for our environmental accountants. This is exactly where strict scientific technical analysis reaches its limits. We have a single pool of environmental damage, a set amount of energy used and emissions created in that unit process, but we have multiple distinct products to point the finger at. Science can tell us the total emissions of the factory, for sure, but science alone cannot tell us what percentage of those emissions belongs to co-product A versus co-product B.
It really is the ultimate allocation puzzle. It makes every single life cycle inventory a massive challenge. When one factory spits out two perfectly usable goods, exactly how do you split the blame? Do you divide the carbon footprint by the weight of the products, by their economic value, or maybe by the energy they contain? Each choice drastically changes how green the final product appears on paper. So, I'll leave you with this to ponder. Next time you see a product marketed as zero carbon or eco-friendly, ask yourself, what else was made in that factory, and who exactly is carrying the rest of the environmental bill? Thanks for joining me on this explainer, and keep questioning the footprint of everything around you.